Hello everyone, welcome back to Mary Maths. Today I'm going to talk about this fourth series, infinite series, and we're going to talk about the radius of convergence and the interval of convergence as well, of each of them. Now for these two over here, we're going to talk about the interval of convergence, and we're going to find a function f of x that defines them. Okay, so now for number one, we have the series from 0 to infinity of x minus 1 to the power of n divided by the square root of n. And well, as you can see, this over here on the top has a power of n, so this is, right, this is going to be, this could be the power series, right? But not necessarily, because we are divided by the square root of n. So we could either use the ratio test or the root test to find out, if this converges or diverges. So let's see, we use the root test. I think the root test will be much easier. So the root test, for the root test we need to find what a of n is. The absolute value of a of n will be, x minus 1 in absolute value, right, to the power of n, and divided by the square root of n. So that's going to be our absolute value of a n. So for the root test, we're going to take the limit as n approaches infinity of the nth root of the absolute value of a of n, which will be the limit as n approaches infinity, right, of the nth root of this expression. So that will be the nth root of absolute value of x minus 1 to the n, divided by root n, Now, it's recommendable that you write the bottom power, as 1/2, right, instead of just leaving it as a square root. And you will see why. It's very convenient, right? So as you can see, n over n is 1. That cancels out. And we have the nth root of n to the power of 1/2, right? So we have the limit, right? We have the limit as n goes to infinity of the absolute value of x minus 1, right, to the first power, divided by n, the nth root of n to the power of 1/2. And we know that the nth root of n over here, as it approaches infinity, right, the limit as that approaches infinity goes to 1. So that is why I took the 1/2 power out, because 1 to the any power is just going to be 1, right? So that goes to 1, which means that the limit will be equal to the absolute value of x minus 1. And in accordance to the ratio, to the root test, we have, values for which this converges, right? If this expression is less than 1, then we're going to find that it converges, right? But then we're going to find those values of x for which this expression is true. So we know that the radius of convergence already will be 1, right? So this will be the center. The center will be at 1, and it will go, it will go like this. So we have 1 over here, right? And then plus 1 is 2, and minus 1, 0, right? So that will be our convergence over here, the interval of convergence, and the radius is simply, how far you go from the center. So the radius of convergence is just going to be 1, right? Now the interval of convergence, in order to do that, because the root test doesn't tell us everything about the interval of convergence, we have to test this a little bit further. So let's see. We have x minus 1, right, is less than 1 and greater than negative 1, which means that x is less than 2, greater than 0. We have to test our endpoints, because we don't really know if it actually diverges over here, because, according to this expression, 0 and 2 are not included, right? So we're saying, well, from 0 to 2, we have all values of x for which this series converges, but we're excluding 0 and 2. So the root test doesn't really tell us the whole story. We have to test these two endpoints. In order to do that, we have to say that at x equals 0, right, we substitute x to 0 over here, and we get that sum, right, we get the sum from n equals 0 to infinity of negative 1 to the power of n divided by root n, And as you can see, this over here will actually, this is an alternating series, right? Because if you didn't have the alternator, right, you didn't have negative n to the power of n, it would just be a p series with p less than or equal to 1, which means that it will diverge, right? But by the alternating series test, this actually converges. Because the first condition, okay, provided that un, right, un equals to 1 over the square root of n, because this is our un, is positive for all n, right, is positive. So if this is greater than 0 for all n greater than or equal to our index, which in this case is 0, actually it's not equal, it cannot be equal to it. Then we can say that the first condition is met. Okay, now the second condition is if this is decreasing, so non-increasing for, okay, the interval, so just eventually, right, if the function will be non-increasing. And that only works when u of n, right, is greater than u of n plus 1. And that makes sense, right? This is 1 over root n. If you add 1 to it, okay, that will be much less than the previous one. And you can prove that by taking the first derivative. Right? You can prove it by taking the first derivative of this. Okay, so if you say f of x equals to 1 over root of x, if you take the derivative, right, f prime of x will be equal to, okay, if you raise this, if you rewrite this as a power, that will be x to the negative a half. So that will be negative 1/2 x to the power of negative, okay, negative 1/2 minus a half will be negative 3/2. And if you plug in any value of x in this function, okay, so this derivative will be negative 1 over 2, okay, x to the 3/2. If you plug in any x value for this negative will prevail, right? This negative will stay, meaning that your first derivative will be negative for all values of x greater than 0, right? That means that second condition is met. And the third condition says that the limit, okay, the limit of your un as n approaches infinity has to approach 0. And that makes sense, right? If you let this equal to infinity, that will approach 0. So all your conditions for the alternating series test are met, so we can say that this converges. Converges by AST, alternating series test. Okay? Now, that means that this is actually included. This is included. So you see, the root test doesn't really tell us the entire, okay, the whole story. Now let's test our endpoint at x equals 2. So at x equals 2, okay, we have the sum, right? We have the sum from n equals 0 to infinity of 2 minus 1 is 1. 1 to the power of n is just 1, right? 1 to the anything is 1. 1 over root of n, which diverges, right? Diverges by p series, okay, with p less than, okay, or equal to 1. In this case, your p will be 1/2, right? Because this is the square root of n. So we know this diverges. So 2 is not included. So finally, we can say that the radius for the series an, right? An has a radius of convergence equal to 1, right? And we have an interval of convergence, okay, equal to, okay, including 0 and not including 2. So from 0 to 2, that's our interval of convergence and our radius of convergence. All right? Now let's move on to question 2. If you're wondering, you could also use the ratio test for this, right? This problem, but it will take much longer. So it is recommended to use the root test for this because, you know, it's much easier to evaluate. Now for this one, I wouldn't say the same, right? I'll have to actually look at, I think the ratio test works better for this. So we're going to do the same thing. So let the absolute value of a sub n, right, equal to, right, the absolute value of x to the power of n plus 1, all that divided by the square root of n plus 3. That will be absolute value of a sub n, because negative 1 to the power of n, right, is the alternator. And when we put an absolute value in it, it's just going to go away, right? It's positive. All right. Now let's take the limit, right? Let's do the ratio test. So for the ratio test, we have the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n, which is equals to the limit as n goes to infinity of This is going to be a sub n. If we add 1 to n, we have a sub n plus 1, so that's going to be absolute value of x to the power of n plus 2 divided by the square root of n plus 1 plus 3. And then we're going to divide this by a sub n, which means we have to multiply by the reciprocal of a sub n. So multiply by the square root of n plus 3 divided by the absolute value of x to the power of n plus 1. All right. Over here we can cancel some things out. So x to the power of n plus 2 divided by x to the power of n plus 1, right? We use the power properties, right? So if we're dividing, we subtract. N minus n is 0, and 2 minus 1 is 1, right? So we have the limit, right? We have the limit as n approaches infinity of the absolute value of x, right? And then multiplied by the square root of n plus 3 divided by the square root of n plus 1 plus 3. And now over here, in order to evaluate this limit, you will say, well, you know, you could do L'Hopital's rule, but that's kind of tedious. So usually what we do is we divide by whatever is the highest, okay, the highest power over here, which in this case is root of n. So we have to multiply, okay, naturally by 1 over the square root of n on top and bottom to just further simplify this fraction. Once we do that, we have, okay, absolute value of x, because it's a constant in this limit, times the limit as n approaches infinity, right? Of, if we divide this by root n, that's just going to give us 1, plus 3 over root n divided by, right? If we divide this by root n, we're going to have the square root of n plus 1 over n, right? Plus 3 over root n. Now over here we could do the same thing. Multiply by 1 over n on top and bottom, and we get, okay, we get 1 plus 1 over n, okay, divided by 1. Okay. Now, if we evaluate the limit already, we know that as this approaches infinity, this goes to 0. As this approaches infinity, it goes to 1. And as this approaches infinity, it goes to 0. So our resultant limit is 1 over 1, which is 1, times the absolute value of x. And we know that according to the ratio test, if we find that the limit, okay, if we find that the limit is, you know, equals to some value, it only converges for values that are less than 1. All right, so that means that our radius of convergence equals to 1. So let's find the interval of convergence, right? So this is true for x between -1 and 1. And of course, we have to test the endpoints because we are not entirely sure, right, if it actually diverges at these points. So at x equals -1, okay, we have the sum from n equals 0 to infinity. -1 to the power of n, -1 to the power of n plus 1 divided by root of n plus 3. Over here we can split this up into, okay, so we have the sum from 0 to infinity of -1 to the n. And then we can split off, okay, a -1. So we have -1 to the n times -1. And look at this. This is -1 to the n squared, which becomes 1. So that just goes to 1, divided by the square root of n plus 3. And that series over there is just basically the -1 times the series, okay, from 0 to infinity of 1 over the square root of n plus 3. And you could kind of know that, you know, you could argue this actually converges, right? Or does it? I mean, it looks like it's a p series with p less than 1, right? If you kind of like get rid of the 3 over here, if you disregard the 3, it's a p series with p less than 1, which means it diverges, right? But we cannot just say that. We have to prove it mathematically. So how about we use my favorite test? Let's use the integral test, all right, in order to test the convergence of this series over here. So the conditions for the integral test are the following, right? So the first condition, right, the first condition is that this has to be positive. Well, we got rid of the negative. The negative is outside, so we're going to disregard the negative. Okay, so it's positive, good. It's decreasing for the interval, okay, from 0 to infinity. Is it decreasing? Well, I mean, yeah, it's, if you actually take the first derivative, right? If you take the first derivative of this, you will see that it will be less than 0 for all values, okay, from 0 to infinity. That's good, okay? So, okay, then we can take the integral, right? We can do the integral test. So let's do the integral test. So we're going to take the integral, okay, from 0 to infinity of our function f of x dx, which will be the integral from 0 to infinity of 1 over the square root of x plus 3 dx. Okay? Now, that's going to be the same as, so let me write it over here. That will be the limit as b goes to infinity of the integral from 0 to b of 1 over the square root of x plus 3 dx. And we can make a substitution. U equals the square root of x plus 3, so that du equals 1 over 2 the square root of x dx. And we know that root x is u minus 3, which means that dx equals to 2 times u minus 3 du. Okay, so we can make that substitution into our integral. So we know that the integral is going to be the limit as b approaches infinity. Integral from 0, okay, if x equals 0, u equals 3. And so this is going to be b of dx, which in this case is 2 times u minus 3 du divided by our u substitution, right, u. And this simplifies to the limit as b approaches infinity of integral from 3 to infinity, right? I mean from 3 to b, we're being formal over here, of 2 minus 6 over u du, right? And you already see that this is going to diverge because of this integral, which will be the limit as b approaches infinity of 2 times u, right, minus 6 ln absolute value of u. And then that's going to be from 3 to b, okay? And as you can see, right, if you substitute infinity into this, that's going to diverge, right? So that diverges. If this integral diverges, right, then that means that the series diverges, right, if we use the integral test. But of course, you might be thinking, why are you doing the integral test? Wouldn't it just be easier to do a comparison test? Well, of course, I mean, I love the integral test. I think it needs some more love. So that's why I did it. So since this diverges, right, then the sum, okay, from n equals 0 to infinity of 1 over root n plus 3 also diverges. And let's do the test, okay? Let's do the comparison test just to make you happy, right? So let's do the comparison test over here. So we could do the limit comparison test because it's more straightforward. I like the limit comparison test. So let's do that, okay? In order for the limit comparison test to be carried out, we have to have an a sub n that's greater than 0 and a b sub n greater than 0 as well for all n greater than or equal to our index 0. If these conditions are met, we can do it. So let a sub n be equal to 1 over the square root of n plus 3, and b sub n, I don't know, let's compare it to 1 over the square root of n. That's the most straightforward thing I could think of. Now, for the limit comparison test, we're going to take the limit of a sub n divided by b sub n as n approaches infinity. And that's just going to be the limit as n approaches infinity of 1 over the square root of n plus 3 divided by 1 over the square root of n, which is multiplied by the reciprocal, which is multiplied by root of n, right? That's just going to give us the limit as n approaches infinity of 1 over 1 plus 3 over root n. This goes to 0, and we get 1, okay? For the limit comparison test, part 1, right, specifically, if we get a value that is greater than 0, then we have to say that if Bn converges, right? If Bn converges or diverges, then An will diverge or converge. So both converge or both diverge, right? So we have to look at the one that we know the convergence of, or divergence, right? So V sub n is 1 over the square root of n, which is a p-series with p less than 1, less than or equal to 1. So it diverges. And if Vn diverges, An diverges. So, okay, it's not included in the interval. So this is not included over here. Now let's test the last one. So at x equals 1, we have the sum, right? We have the sum from n equals 0 to infinity of, right, negative 1 to the n times 1 to the n plus 1, which is just 1. So negative 1 to the n divided by the square root of n plus 3. Now, we know this diverges, but this over here actually converges by the alternating series test. So this converges by AST. That's because, right, all conditions of the alternating series test are met. We have un equal to 1 over the square root of n plus 3, which is a positive, right, positive function. Also, it's non-increasing for all values from 0 to infinity, or eventually it's non-increasing, right? That's what the theorem says, right? If it's eventually non-decreasing, like that doesn't mean it has to be, you know, strictly non-increasing from 0 to infinity. It could be non-increasing from 5 to infinity, from 1,000 to infinity. But if eventually it is non-decreasing, then we can say the condition, that the second condition for the AST is met. The third condition, right, is that this has to approach 0, and it certainly does. Okay, so that converges, so it means that we have to include 1. So finally, we can say that the radius for the series A sub n, okay, the radius of convergence, equals to 1, right? And the interval of convergence is going to be, right, parentheses, from negative 1 and then to 1 included. All right, so that's going to be it for this one. Now let's move on to the last two problems, which are quite interesting. All right, for problem number 3, we have the sum from n equals 0 to infinity of 3 to the n times n to the n, right? I'm sorry, x to the n. Yeah, I'm sorry, there you go. Okay. And we want to find the interval of convergence and the function that describes it. Okay? So let's rewrite this. Since we have the same powers, we have the sum from n equals 0 to infinity of 3x to the power of n, right? And this is very, very similar to something we have seen before, right? It looks like a, right? It looks like a geometric series, and we know that if we have the sum from n equals 0 to infinity of a, right? Suppose a x to the n, right? This is going to converge to to a over 1 minus x, right? And let's say a is 1, so if a is 1, that's just going to be 1 over 1 minus x. All right? So this is actually very similar. So we have to, okay, according to theorem 21, if we have something like this, and we have a function that is very similar, right? We have a function, we have a series, right, of a function, f of x, to the power of n, then, okay, the function that describes this will just be, right, 1 over 1 minus f of x. So, our function over here is just going to be, right, 1 over 1 minus 3x. That will be the function, because it's a geometric series, and it only converges for values less than 1. Okay, now let's find the interval of convergence, right? So we could easily do a root test. That's the easiest thing I can see. For now, right, the root test will be the root of a sub n, the absolute value, as it approaches infinity. And, well, we have to say that a sub n, the absolute value, will be the absolute value of 3x to the power of n. So we have the limit as n approaches infinity of the nth root of 3x to the power of n. This cancels out, and we have that this is equal to 3x in absolute value, right? And it converges for values less than 1. Okay? So we have x less than 1/3, greater than negative 1/3. And we have to test the endpoints, right? So at x equals negative 1/3, if we plug that in there, we have the sum, right? We have the sum from n equals 0 to infinity of, right, 3 to the n, or 3 times x, which in this case will be negative 1/3 to the n. This becomes negative 1. The sum of negative 1 to the n diverges, right, because it's just oscillating from 0 to 1. So that's just going to, okay, that's going to diverge. Diverges, right? It diverges by the nth term test, by the, if this is like a geometric series, right, then you will say this is 1 over, right, if your r is not less than 1, right, strictly, if it's not less than 1, then it's going to diverge. So that diverges, so negative 1/3 is not included, but 1/3, well, let's see, for 1/3, so at x equals 1/3, we have the sum from 0 to infinity of 1, right? 1 to the n, that's just 1, which also diverges. It's just adding 1 every time. Okay, so that means that the interval of convergence is just going to be from negative 1/3 to 1/3, not included. Okay, and the function is 1 over 1 minus 3x. Now for this one, let's see what we could do. Well, this one is actually quite interesting. Let's see what we could do. We have the sum, right? We have the sum from n equals 0 to infinity, okay, of x squared minus 1 over 2, all of this to the power of n. Now, how are we going to find the function? Well, let's worry about that later. Let's find the interval of convergence, right? For the interval of convergence, we could do the root test again, right? The root test is the easiest thing. So a sub n, absolute value will be the absolute value of x squared minus 1, right, to the power of n, all of that divided by 2. So we take the limit as n approaches infinity, right, of the nth root of the absolute value of x squared minus 1 to the n divided by 2. Now this nth root, right, this nth root will cancel out with this, and then we're left with 2 to the power of 1/2, right? So that's just going to give us the limit as n approaches infinity, right, of the absolute value of x squared minus 1 divided by 2 to the power of 1 over n. Okay? And well, look at this. As n approaches infinity, this becomes 0, right? 1 over infinity is 0. 2 to the 0 is 1. So we have that the limit will be equal to x squared minus 1. And we know it converges for values that are less than 1, right? Okay. So we could solve this, okay? We could solve this. We know that if we solve this over here, we have x, okay? We have x squared minus 1 less than 1, right? It cannot be, can it be greater than negative 1? Well, not really, right? So we have that, okay, x squared is less than 2, okay? So that x is less than the square root of 2. Okay, so the square root of 2. So those are the values for which this will converge, right? So let's see if it actually, okay, if it actually works out for that value. So at x equals root 2, right? At x equals root 2, we have, okay, the sum from n equals 0 to infinity of root 2 squared minus 1 over 2 to the power of n. Root 2 squared is just 2, 2 minus 1 is 1, 1/2 to the n, right? So that's going to be the sum from n equals 0 to infinity of 1/2 to the power of n, which is a geometric series, convergent, okay, geometric series. So that converges. Okay? So we have to say that the interval of convergence, right, the interval of convergence will be from negative infinity to root 2 included. Okay? So that works out. All right. Now, how are we going to find the function? Well, the function has to be something like this, right? If we know that the sum from n equals 0 to infinity of if you have, x to the power of n, that's just going to be 1 over 1 minus x, right? So if we use this fact, okay, to take advantage of this over here, so we could say that this will just be, right, this will just be 1 over 1 minus, okay, x squared minus 1 over 2. So this should be our function, right? So this is going to be, that's going to be 1 over 1 minus, if we actually find the common denominator over here, this will be 2 minus x squared and then plus 1, which would be 1 over, and the 2 goes to the top, right? So that 2 goes to the top. So that'll be 2 over 2, right? And then 2 plus 1 is 3, so that's 3 minus x squared. So that's your function. And then your interval of convergence from negative infinity to the square root of 2. Okay, now let's see. From negative infinity, so if you plug in any value negative infinity from here, that just looks like it's going to diverge, right? Yeah, that wouldn't make too much sense. So let's see, what did we do wrong? This should be this should be less than 1, okay, and greater than negative 1. Yeah, I think that was wrong over there. So let's see. So if we add 1 on both sides, right, we add 1 on both sides, we get 2 over here, we get 0. Yeah. Okay, so from 0 to 2. So it's actually from 0 to 2. Yeah, and at 0 we have negative 1 over 2 to the power of n, which also converges. So it's actually included. So my apologies, it's going to be, okay, from 0 to 2. From 0 to the square root of 2. That will be the interval of convergence. All right. Now let's see if we have another problem. I think there was an extra problem that was worth looking at. Yeah. So we're given a function, right? So we're given a function, and then we're asked to find the series. So that's pretty interesting. Let's see. We have the function f of x equals to 5 over 3 minus x. Okay, and we also have the function f of x equals to 3 over x minus 2. All right, and then we're asked to find the series. Right? So we know that for a fact that 1 over 1 minus x will converge, right? So that's going to be the sum from n equals 0 to infinity of x to the power of n. So that's our power series over there. So we kind of want to have this over here in this form, right? So it doesn't matter what's in here, as long as we have 1 on top and then 1 minus something on the bottom, we'll be okay. So how about we start with this one over here? So if we start with this one. We could kind of manipulate this, algebraically, so that we have 1 and 1 minus something on the bottom. So, well, let's see. What if we have, right? We have 3 on top, but we have 2 on the bottom. What if we had 3 on the bottom? We could divide by 3 on both sides, and then we have 1, right? That's pretty clever. So let's see. So we have f of x equals to 3 over x. And then let's see, we went 3, right? So minus 2 plus 3, but because we're adding 3, we have to subtract 3. So look at that. negative 3 minus 2 will give us negative 5. So f of x equals to 3 over 3, and then we're going to have plus x minus 5. Look at that. What's next? Let's divide by 3 on both sides, right? The entire expression. So we have f of x equals to 1 over 1 plus x minus 5 over 3. And this essentially is in the form of 1 over 1 plus something. Well, not really. We want 1 over 1 minus something. So let's take out a negative. So we have f of x equals to 1 over 1 minus, right, 5 minus x over 3. So essentially that's the series from n equals 0 to infinity of 5 minus x over 3 to the power of n. Okay, so that's it for this one. Now this one, okay, we kind of do the same manipulation, right? So we want 5 on the bottom, right? Because we have 5 on top, and then we divide by 5. So we have f of x equals to 5 over, we want to add 2, so we have to subtract 2. So we have 3 plus 2 is 5 minus x minus 2. Look at that. And that's f of x equals to 5 over 5 minus x plus 2. We divide by 5 on both sides, and we have f of x equals to 1 over 1 minus x plus 2 divided by 5. So f of x equals to the sum, right, from n equals 0 to infinity of x plus 2 over 5 to the power of n. And that concludes, okay, my review of this series, power series, geometric series, and so on. Thanks for watching. I hope you found this video helpful. I'll probably be posting a Physics 111 review for the common exam soon. So keep a look on that. So see you next time.